Okay, shall we begin?
All right, so this is just a continuation of our 2020 Formula 110 final project presentations. And so, Team 3, take it away, introduce yourselves, and let's.
So we're team 3. I'm Luca.
I'm Soumya.
I'm Anav.
And we're the Roadrunners. So our presentation is going to go over kind of the different approaches we use for each milestone, and then stuff we didn't really end up using any of the milestones, but thought was cool that we discovered anyways.
Yeah, so starting with the milestone 2. So the foremost important thing to note was that it was only based on evaluated only based on the time for laps, and there were no obstacles. So trajectory optimization was obviously the first thing to be done, and so we went ahead and did the CMIS for optimizing the race line. So this began with sparsely sampled centerline points for the CMIS reference. So the center line was given, so we just sampled some points from that, and instead of doing a box constraint or any other types of transformation which would reduce it to one-dimensional search space, we just went ahead and did it in polar form. So there was no transformation involved, and we could just easily, like in a couple of hours, get the trajectories ready. So this simplified the constraint formulation a lot, and CMIS trajectories were obtained like this. So the CMIS solution that was obtained was a regularized spline was fit on that, and we calculate the fitness by the time it takes for the car, the approximate time it takes for the car to complete the loop, and velocity was profiled based on the curvature. This in a way led to a minimum curvature trajectory, but the regularization on the spline helped a lot to make it even smoother and better. So finally, when we have the regularized spline, we sampled 500 points for the pure pursuit track. Next slide. So this was the CMIS trajectory that was generated versus the center line on the left. And you can see it's much shorter than the center line itself, and the fitness curves on the right denote the fitness score versus the CMIS iterations. So it reduces by a lot in the beginning, and then just fine tunes itself to get a better time. Next slide. So, and finally, we track the waypoints using pure pursuit with look ahead, and we always go at full speed instead of any curvature or dependent speed profile because we could, and it was evaluated only based on time. So we thought there was no point slowing down, and so there was no drift control. And this is the video how we won that race. And let's start with the milestone 3 approach.
Yeah, so in Milestone 3, we built upon the RT star approach we used in the previous lab, and we made some changes to it to make it work better. So, for example, we had a angle constraint in the steering function, and we used path freezing because we noticed that the RT trajectories have a lot of variance. So, and since all the obstacles were static, we committed to an RT trajectory until it was either complete or there was some new detection which causes a collision. So we use peer pursuit to track the RT star trajectory, but we had some issues with it being able to track reliably. And since it was a single-threaded approach, our algorithm was quite slow, and this was something we learned to fix for the fourth milestone. On the next slide, we have a video.
There we go.
Right. So as you can see here, once we find a good path, we just commit to it. And you can also see the early termination here, which is that if we have directly found a path to the goal, we just go there instead of building an entire RT star tree. So this, I think, mostly worked, but it wasn't a great approach, and it wasn't good at all when it comes to racing, which brings us to the motivation for model predictive control in the fourth milestone.
For the fourth milestone, the overall idea was to select a trajectory. So we have a global path, and then we choose a local path which is dynamically feasible, and we track that using MPC controller as a reference tracker instead of pure pursuit, because it could handle dynamics and we could add constraints as desired better. And in the end, we'll talk about lane switching, which helped us overtake with the overtaking maneuvers. Next slide. So for the trajectory selection, we generated a few dynamically feasible trajectories offline. So they look something like the picture on the right. So this is how these are minimum these are constant curvature trajectories. We set the velocity, like these are generated at with the time step of 0.01, which was the simulator step size, and we run it at fixed velocity with a fixed steering angle, and we sample some number of points depending on the desired horizon. And once we have these generated curves offline, we use these to track the global CMAS trajectory. The CMAS trajectory used here is not the same as the one we used in Milestone 2, because that was cutting too short and too tight around the corner. So this is similar but much safer, and we use alternate parallel lanes, which use of which will be explained later. Next slide. So the path selection was based on any local path which would maximize an objective. The objective was basically to increase the closeness of the endpoint of that trajectory to the global path, weighted with the progress maximizing aspect of the path. So progress maximization was depending on how far the point was from the current position, and we do the incremental index thing to prevent reversal. So in case when car is oriented such that it is normal to the curve, it has generally two options to go backwards or forward. So we make sure that it increments always to prevent it from going in reverse, so to make it more robust. Next slide.
So to track these paths, we used an MPC controller. And our cost function it's just a quadratic cost function. We had, which I'll talk about in a sec, but we did just a super simple model of X, Y, and orientation for the state, and then V and steering angle for the inputs. And we basically didn't penalize orientation at all. We just wanted to follow the path. And so for each the goal for each horizon time step was a point along the path, not just the final point. And so it made a nice curve. And then the desired velocity was set to 4.5 meters per second with a steering angle of 0 for that input, so that it would try to stay going fast. We found that if we set it to 0, it would go about 4.2 meters per second average, whereas if we set it to 4.5, it'd go up to 4.5. So MPC required some constraints. The dynamics of the system were done with just the simple XY orientation and then velocity and steering angle input, linearized at every time step. And we were able to, I think we got up to horizons of 50 steps, and it was the linearization, while it kind of got worse as you got farther along, it was accurate enough for when our MPC didn't finish on time. So then we also had a steering versus velocity constraint to prevent skids. So we took the kinematics or the physics model from the simulator and basically ran a loop of a constant velocity and constant steering angle, and then the slip angle would eventually stabilize to a one number, and then that's what's plotted on the left. And you can see it's kind of it's not really linear. And then, so on the right, it's that's a slip angle of 0.3, or I think negative 0.3. But so we can make a half space that approximates that, which is what the red line is. So as long as we stay on the lower side of that red line, we shouldn't slip more than 0.3 radians, or have a slip angle more than 0.3 radians. In the end, we found that using that constraint for actual racing didn't help that much in terms of preventing collisions. All it did was slow us down. So we ended up turning that up to infinity, but we tested with a few different things. When there's obstacles that are much closer versus just having a single car to race against, it was more beneficial. And so to pass other cars for actual racing, we needed a way to figure out to overtake. And so we went with lane changing. So these lanes are basically just the CMAS trajectory expanded out concentrically. And so we ended up with 5 paths, I think separated by 0.25 meters out each. And effectively what we did was, if the path that you're currently on is blocked, both forward and backwards a bit, depending on the situation, it would search for the next best path that you could switch to. And then it also had a little distance tracker that it would try to stay on that path for an additional, let's say, 3 meters before checking for a new, checking if it should come back. That way, as it came out, it would then stay there for a bit before trying to cut back in immediately. Otherwise, you could end up with some situations where it just oscillate in and out if the car in front of it's slower. Some other features we ended up doing, we used multi-threading to do the to publish the drive message so that it could keep publishing even if MPC hadn't finished. And then it would just publish the rest of the optimal trajectory for MPC. Of course, since the linearization was from the original one, it might not have been perfectly accurate. So that was open loop, but that allowed us to keep running. But our MPC was also plenty fast because we used such a simple model with 50 horizon steps. We were getting like 60 hertz, so it didn't really matter all that much. But if the optimization, for example, didn't work in one step, it didn't have any issues. And then we also implemented some visualizations to help us debug MPC, because MPC, looking at a bunch of matrices is kind of hard, especially when the horizon is large. So in the picture, you can see there's a little blue line with a red line on top of it, which the red represents the throttle. And then the black is kind of the steering angle to represent the tire. And then we have the lanes plotted as well. That's what the red dots are the CMAS trajectory lane that they're following. Here's what lane changing looked like. So you can see it's avoiding obstacles, and by switching lanes, I mean, it's also just avoiding obstacles using the trajectory, but the lane itself switches to help avoid those obstacles. We don't have a video of the overtake right now. We just didn't have time to take one, but it did overtake cars that are slower than it. But like Team 2 mentioned, if the car is similar speed, it just kind of hangs out.
Yeah, so this is just the miscellaneous section of the presentation where we're going to share some of the things which we discovered during development but didn't necessarily make it to the final project. So our testing methodology was to first test in the one-person simulator, which we're using since the beginning of the semester, find any edge cases and try to fix them. And the convenient thing is we can run it using the debugger. Using the VS Code debugger, it's especially easy to figure out when things are going wrong. Then we run in the two-player simulator, and we also tried racing against our old agents. And that's where we discovered some of the problems with overtaking, for example. Yeah, look on next slide. So this is about some of the stuff which we tried out but didn't use in the final project. So for example, for prediction, we tried using a Gaussian process, which is trained over a bundle of CMES trajectories. So a Gaussian process is like, it's a machine learning model, which is kind of similar to a KNN or kernel regression. But the nice thing about a Gaussian process is that it will also give you the confidence of the prediction. So unlike kernel regression, which just gives you an output, this gives you the confidence of that output. And that can be quite useful when you're predicting something, because if you're not very confident in your prediction, you can switch to using a linear model, for example. So in this case, it predicted dx by dt and dy by dt, and that gives you the trajectory basically. But the shortcoming of this is that you need to have a good prior of the other vehicle's trajectory. And if you don't have one, the prediction is not very good. And the model size is very large. So it takes nearly 1.5 GB on disk, but 3 GB at inference. I'm not really sure why. And this made it kind of difficult to incorporate with our planner. Then we also tried half-space constraints for MPC, first by using a method similar to follow the gap by using a cone of feasible half spaces. But we later realized that this wasn't really required since we were avoiding obstacles from the outset. And we weren't able to formulate the problem of having time-varying obstacles in the MPC horizon. Next slide, please. So this is what so in case MPC didn't work out, we tried improving RT star. And some of the things we did was we tried regularizing the cubic splines, which makes the trajectory smoother. And we also tried using the shortcutting approach described in this paper, which made the trajectory shorter. It's shown on the next slide, actually. So here in red, we have the spline interpolated RT star trajectory, and in purple, we have the shortcut trajectory. The problem with this was that we couldn't get MPC to track this trajectory very well. And in fact, it wasn't working at all. So we weren't able to really try it out much. And then on the right, we have the set of trajectories we use for training the Gaussian process model. Actually, on the next slide, we have a video of how it works in action. So over here, we're tracking the orange car. And the green line is its future trajectory, I think, over the next 100 time steps. And as you can see, there's some sections where it's actually able to predict quite well. But in some parts, like at the bottom of the track, especially at this part of the track, actually, you can see the prediction becomes bad, probably because we didn't train on too many trajectories there. And I think, yeah, like it might be something interesting to look at if we were to develop on this further. But yeah, we weren't able to use it in our final project. Yeah, so this is some of the learning experiences which we had when developing this project. So one thing which we realized is that dynamically feasible RT star is hard to get right. This is something we learned from the first lab itself. It's difficult to find a good velocity and steering angle combination for an RT trajectory. Then we learned to start simple before trying out anything complicated. And what really helped us in developing this project was using classes very liberally in our C++ code base. So this made our code very modular, and it also made it easy for us to develop because we could split the work without interfering with each other's changes. Using visualizations helped a lot with debugging, and we had to use the right tools for programming and collaborating online. We didn't implement unit tests, but now I see the value of it because we would have saved a lot of time instead of manually testing all of our changes. And one of our teammates who chooses to remain anonymous says that brilliance is knowing when to stop. And I think it's especially true in this kind of project because we had so many ideas, but it was difficult to tell which ones we should actually use in the final project and when to stop developing because we just wanted to keep improving what we were doing. Yeah, so this is also something interesting which we realized, which is this car over here is moving very fast. It's moving at, I think, 7.5 meters per second, but there's no drift at all. And this is actually done by driving the car in reverse, probably because the simulator doesn't account for high speeds in reverse. But I don't know if you can call it a race strategy, but it would have been very interesting if a team tried it out. Then yes, we would like to thank the TAs and professor for giving us this experience. Despite everything being online at the last moment, I know it must have been very difficult to shift everything and change the format of the course, but we still managed to get a good experience with developing this project, and we learned a lot on the way. Again, this is a quote from one of our anonymous teammates. And now it's time for questions, comments, and concerns about the project. We can take some from the chat if there are any. So one is, how did you decide to stop following a frozen path? I think this is with reference to RT star. And we decided to stop following a frozen path either when we're almost at the end. I think it was when we are half a meter from the end of the path, we start searching for a new one. Or in the other case, it's I think if the current path ends up becoming not collision free anymore because of new scan data, which surprisingly happened quite often. Then the next question is, did you compare RT and lane changes for overtaking? We couldn't get RT working well enough to actually try it using lane changing, so we weren't able to compare it as such.
Yeah, and also the RRT paths were not very dynamically feasible, so we decided to not use them at all. Instead, go for lane changing.
If you go back to where our RT video is, let's see, go back here. You can see that it goes real wide around some of these obstacles. Well, that's not one of them. Let me skip forward. Here, for example. So I don't know how much better it really would have been.
Yeah.
So with shortcutting, that problem was kind of fixed, but again, it was hard to get our MPC to actually track the RT trajectory. In terms of tools, I think it was pretty standard what we used, but it's just that using VS Code, for example, I think was good because of the visual debugger. We use Git, of course, for project for version control. And
I think visualizations helped a lot. So developing visualizations made debugging way too easier.
Writing some generalized,
yeah.
Writing some generalized visualization code that you could use in any class to implement some sort of visualization faster made it really convenient to visualize things. And then having a bunch of branches for different features you're trying in Git really made things easy to clean up when you screwed up.
Yeah.
Any other questions?
So did you guys have any kind of like sort of big red button safety controller? If you get too close, it goes full brakes, or is that just all handled in your MPC portion? Where is that handled and how?
It's mostly handled in the MPC controller and local trajectory selection. So the trajectory selection would always be like the best it can and collision free, and MPC can track it very well. And otherwise, there were cases when the opponent, which was blind, the default opponent was blind, and so it could just cut us in. So in those times, we preferred slowing down to make it more robust as a safety measure.
Mm-hmm. Can you be more clear about how you check for collision free? Do you have a prediction of the other car with like the pure pursuit method, or is it just at this moment in time?
It just does that in that moment of time. We do not go for prediction approach in this case because, yeah.
Well, one thing specifically that it wasn't exactly prediction, but it was the closest we could get in the time we had, was for lane changing when we, if we're not if our current lane is blocked and we decide to switch lanes, we would check not just if the lane in front, so there's a certain horizon in the lane that would check for in meters, and also behind to make sure that there's not a car in the lane behind that it's going to cut in front of. Mm-hmm. That was the only sort of prediction we had implemented. But it did sort of work. It didn't cut off the car as much anymore once that was implemented. Like previously, it would do some pretty bad things, but that helped.
Yeah, and the refresh rate was very fast because MPC could solve it way faster, but that might have been a problem if we were to implement on real car.
So one way that at least Billy and I have looked at sort of how safe is my solution in the past is to measure the minimum time to collision over the entire lap. So you could think of on one hand, you want really small lap times, but on the other hand, you want reasonable TTCs at all times. So sort of a plot of those things on the two axes is pretty useful way to compare your different solutions.
That's interesting. Yeah.
I'm also I'm enjoying these talks. I think people have spent an incredible amount of effort on these projects, so very happy about that. I wish that we had the real cars because I would love to see how much better MPC works than pure pursuit. I think that's should be maybe the default solution in the future to path tracking.
I realized that MPC was actually working very great, and it was the simple model was like unexpectedly working flawlessly, and linearization like we didn't face any problems with the model as such.
Yeah, so the reason I want to see it on the real car is that when you know the actual dynamics 100% for sure, it does make your predictions a little bit better. But I think the model in the simulator is pretty accurate.
After first race, since we didn't have the braking on, we actually decided we might calculate the dynamics for the car for finals, but then we didn't get a chance.
Yeah.
In terms of actually cutting off our opponents, we did have it so that it wouldn't. So originally we were checking, one thing that we'd like to change, the codes there, just the settings aren't tuned, is that so if the car from behind you gets too close to it from behind, it'll sometimes move out of the way into another lane. It's very polite, but it's not necessarily a good race strategy. But there is a pretty simple way to change that. It's just not in our current implementation.
Well, it's better than crashing.
Yeah.
Well, it's not our fault in that case. It's them hitting us from behind, you know.
Yeah. From the instructor's perspective of buying the lidars, we like it, but I understand what you're saying.
Thank you very much.
Yeah, thank you.
Good job. Good job.
Thank you.
Let's go to team 4. I think compared to last semester, there's a clear kind of understanding now with the benefits of adding each approach. I think when the last semester it was really like let's take these and let's see how well they go. But here you can see with CMAES you have a very clear benefit. With MPC you have a clear benefit. Your racing strategies of picking your paths have had a clear benefit there. All right, room 21. What is 21?
So 21 is basically like the jersey number of one of our team's players. So that's why and Room is the nickname that the fans have given him. So that's why it's Room 21.
Cool. All right. Introduce yourselves and then get started.
Yeah. So we are team 4. I'm Akhilesh, and my teammates are Mihir and Veki. The main inspiration behind these races was that when you want to navigate through uncertain environments, you need a good planning strategy as well as a good control strategy in order to track that plan that you've formulated. Also, in most of our previous labs, we've been following just one set of waypoints, which sometimes may not be the best strategy because when you're tracking one set of waypoints, you need to slow down when the opponent car comes around you because you're following one point and you don't have any other track to follow. Also, if you get sandwiched between a wall and the opponent, then there's a very high chance of crash. And also, it becomes very difficult to overtake when you have just one set of waypoints. The different control strategies that we thought of while for our project was pure pursuit, obviously, wherein the dynamics and workspace constraints are not considered at all, and it just tracks the waypoints that you've given. While on the other hand, MPC uses the dynamics and tries to track a dynamically feasible and locally optimal trajectory. So how we went about implementing our project was to have a multiple set of waypoints along the racetrack, which was done completely offline. So we had for our project we used 5 set of waypoints in order to um, basically have some kind of a lane changing strategy. And then the online approach had the planner, the generating the workspace constraints using the prediction as well as finding the safest gap based on the constraints. And then an MPC tracker, which would use this reference trajectory and reference inputs to give the best set of control values, which will be published and then published as a drive message. So for the offline process was basically done by generating multiple strategies with respect to a center line. So we found 5 tracks on each side at a gap of 0.25 meters from each other. This 0.25 meters was taken into consideration by looking at like the overtaking by looking at an overtaking strategy. So when you're behind a car and you want to overtake, you need to have um, a, a point to track that is nearby, but also not having a very high steering angle because we have steering angle constraints. So 0.25 meters kind of worked pretty good for us. And also the reason we just used 5 out of these 10 was to reduce the computation time required to find the best waypoint, as you will know later. So these were the kind of tracks that we generated. So these are just the two on each side, but we had 5 on each side before choosing which ones to track. So the online process was something like the planner would get the dynamics of the car, predict the opponent's path, use the predicted path to update the static map that we have. So basically, we predicted the opponent's path and blocked those occupancy grids as obstacles in the cost map before choosing the best waypoint to track. Once we got the best waypoint, we then generated a reference trajectory towards that waypoint and then passed it on to the MPC tracker to generate the best control inputs. So this was kind of the overall strategy that we used for the race. So as I said before, we had 5 different tracks to choose from. So what we were doing was at every time step, we were looking at all the 5 different tracks and choosing the best waypoint from each track at a particular look-ahead distance. So since we have 5 tracks, we get 5 waypoints for each instant. Once we get these 5 waypoints, we do a feasibility check to choose which waypoint to follow. And this feasibility check was done using basically collision check. So the line joining the current position of the car and the waypoint that we've chosen was discretized into I think it was 20 points, and we were checking whether all the points are collision free. Also, we were checking the steering angle value so as to make sure the car doesn't slow down suddenly when the steering angle is too high. So we had a threshold so as to just choose the um, waypoint which is closest to us. And then the predicted path of the opponent car was also used in order to update the cost map every time and choose the waypoint which doesn't fall in the obstacles, basically. In order to generate, once we got the best waypoint that we want to follow, we wanted to generate a reference trajectory for the MPC tracker, and we experimented with three different trajectories. The Dubin's path was this is the Bezier's curve, which was kind of working fine, but there was certain cases when the the car would choose a waypoint which is slightly behind the car, or sometimes very near to the car, which would sometimes would give us a weird kind of trajectory, and the MPC was not able to track it accurately. So the Bezier's curves, if um, it uses a cubic polynomial fit. So we were giving it three different points apart from the current waypoint, which were at a 1 meter distance from each other. So that was how we were getting the Bezier's curves. We also tried experimenting with Dubin's path, and as you can see in the picture, this was why we did not go ahead with the Dubin's path. And The reason why this was happening was because the Dubin's path depends a lot on the current heading of the car. So if the heading is not in the direction of the waypoint that you want to track, it tries to take a whole loop to go to that particular point. So that was not exactly feasible uh, for the constraints that we were choosing for our MPC. And also, we were finding it difficult to generate a Dubin's path and then check collision for that, and then regenerating a better path. So that was another reason why we did not choose to go through with Dubin's path. Yeah, Mihir will take over from this and explain the reference trajectory and the MPC part.
Yeah, so since Dubin's path and Bezier curves did not work, like in the sense that the path given by them was like sometimes causing the MPC tracker to generate infeasible solutions. Could you go back a slide? Yeah, so in what we were doing is we were just integrating the dynamics for that to get the reference trajectory in the final implementation. So what we were doing is like we were getting the best waypoint at a particular instant to go at. What we were doing, so we are finding the steering angle to go there, and so we have the initial state from the current pose. What we do is we take inputs for certain time steps and time steps, and those inputs were decided by like this. So we have a certain current velocity of the car. We assume that the car will keep accelerating with the maximum acceleration until it reaches the maximum velocity it can go at. And the steering angle was interpolated based on the final steering angle required for like the angle with respect to the waypoint, and that interpolation was done in the way that it will take a higher angle at the like for initial time steps, and like as the time steps keep increasing, the steering angle is getting lower. So like the pipeline we were using to get the reference trajectory, we were using the same kind of pipeline to get the path traced by the opponent. So in this case, we are assuming that the opponent is doing the pure going with the pure pursuit control on the center line. So I think the video is like placed at the wrong place. So like there was an image behind that like which could show what was the path predicted by the opponent in our case. And like once we get the path, like once we get the poses of the opponent for like the next n time steps, we update those poses as static obstacles on the occupancy grid map, and like we add some padding to make sure like the width of the opponent car is considered as well. Next slide. Yeah, so so once we have the reference trajectory from the planner, like we tried two tracking approaches. One was like just pure pursuit, and the second one was like using MPC, since like MPC considers the cost which we like the deviation from the reference trajectory, and also the constraints, the dynamic constraints. So I'll start with MPC first. Yeah, so like this was how MPC was running. Could you go back? Yeah. With the reference trajectory which we got from the planner. so it was able to track it pretty well. Next slide. To get the workspace constraints, what we were doing is instead of using parallel lines as like workspace constraint, which would have been better. To simplify it further, what we were doing is like once we have the best waypoint, we used to search for the largest gap around that waypoint. So we basically used to go on the left of the waypoint, and like we used to get the scan values, and we like will search the first point on the left, which is which is like below a certain threshold, and we'll like fix that point. And similarly, we'll go on the right, and the line like it forms with like the rear wheels. We used to form a half space constraint using that. So could you just go one ahead, like, yeah. So the resulting gap formed we were using as the workspace constraint for the MPC. So and like, yeah, so we express those 4 points into a half space constraint in the form of ax less than equal to b, since MPC expects that, like, for solving that. So this was a problem formulation. So once we have the reference trajectory, we define the MPC cost as like the deviation from the reference trajectory as well as the inputs. And like to fix the constraints, you like the initial state should be the same as the current state, and we had linearized the kinematic car model like around the reference trajectory, and we were using the discretized system of that. And and one more thing is like the solution generated by MPC should always be within the workspace constraint defined in the previous step. And also like we had the constraints on the input, which were like defined by the maximum velocity and the minimum and maximum steering angle. So we converted this into a quadratic programming problem, and then we use like OSQP icons to solve this. So to debug our MPC implementation, we use the old simulator, wherein like you can see it working on the left with the visualization of the constraints, half space constraint changing like at every time step, and on the right is just like the car moving along is obstacle maze which we created on the previous simulator. So it was able to avoid obstacles pretty well. And then like the so next step was to like make it work on the multi-agent simulator. So this is how it worked with the on the like the two agent race. So you could see like the red lines define the workspace constraint. So when the ego car is ahead of the opponent car, like it will have like everything within a certain angle of space. And so the green point is the best waypoint is following based on the feasibility check. So it keeps going along then, and like when it encounters a situation when the opponent car is in front of it, so the workspace constraint ensure that it doesn't go and crash into it. Like you can play again the start of the video to just show the overtake again.
Yep.
Yeah, so you could see the two red lines. They are making sure like the constraints are in the gap. So MPC worked well for us, but there was a problem in the situation when like the gap, like when our car was close to the wall and the opponent car was coming inside. So in those cases, since the way of we are finding the constraint is like we are going on the left, on the right of the best waypoint and choosing the best gap. In those cases, the gap used to be pretty small, and like MPC did not give any feasible solution. Like we countered that problem with like tracing, like we used to publish the solution from MPC on like using different message, and then we had another node which was executing the path as long as it got one, and if it did not get a path one, it will keep executing the previous one. So like we were able to counter that, but in the cases when there were turns, because since the car the publisher to the drive was executing the previous solution, it like the car went like did not take the turn and like just went straight, and like it was difficult to recover, and it was like making it slower in the racing strategy. So we tried to see how the pure pursuit control works out, and we found that like MPC was better when it comes to like tracing the reference trajectory, but pure pursuit was more reactive in the sense that when the opponent car was very slow, it was able to make sure it doesn't collide, and like it was able to handle the turns. So in the final submission which I have made, like we have used the pure pursuit one. So this was the pure pursuit code running 128. Yeah.
Another feature that we had tried to implement here was that when the opponent car comes very close to our car, we go into a low speed mode so that we don't go and ram into the other car. Basically the constraint was that if the opponent car is ahead of us and within a certain distance threshold, we slow down, and as soon as we are ahead of the car, we just go back to the high speed mode so that we can efficiently overtake the other car.
So to answer
Yeah.
the questions, so one question by Chetan is how much did Spline improve the ability for your controller to track the reference path? So so Spline did not affect the ability of the controller to track the path. It was like if we did not use Spline, like then it was the case, then we are like just doing pure pursuit using MPC as a controller. Like we need to define a smooth trajectory for the controller to trace. Let me know if you have any follow-up question for that. And there's another question by Soumya. What was the backup if all paths were
So
blocked?
it
Yeah.
wasn't totally clear to me what spline did you end up using in the end? You used the Bezier spline or Bezier curve or
So we were integrating dynamics to get the reference path. So like at a particular instant we had the best waypoint. So based on that, let's say I'm predicting for the next 5 time steps. So I'll define a velocity for the next 5 time steps, and I'll define the steering angle for those 5 time steps, and I'll just integrate the dynamics to get the next point poses.
okay, so you like pick a steering angle at time step 0 and a velocity. Forward simulate, you have a new pose and you get to pick a new steering angle and velocity.
Yeah.
Okay. And so then you're solving, find me the steering sequence of steering angles and velocities that get me to the goal point.
Yeah.
And what method are you using to solve that?
Uh, like for solve what? So once we have the reference trajectory, we use MPC to trace that.
Okay, you get the reference trajectory.
And we
How?
define the cost, MPC cost, as the deviation from the reference trajectory.
Yeah, but sorry, I think I'm confused. How did you get the reference trajectory? What form is it?
I'll just go through the slide again, Akhilesh.
Yeah.
One slide back. Yeah, so at a particular instant, we have that in this visualization, you can see in the with the green marker, the best waypoint to go at. So we get so we find the angle required. Let's say if it doesn't take a smooth trajectory and just goes directly there, we find that angle, the car heading mates with the waypoint position, and we interpolate those steering angles for uh, end steps in between, and that interpolation is done considering that the car will take a higher steering, like let's say the steering angle is 0.6 to go there. So it's so exponentially it's decreasing the steering velocity to go there. So it will start with let's say 0.3, then it will go 0.2, 0.1, and then it will become 0 eventually. And we use those and the velocities as the inputs, and we integrate the dynamics.
Mm-hmm. So it's kind of like pure pursuit.
Yeah, so in pure pursuit it was directly going at the particular angle. In this case, we were giving it a smaller angle at each time step.
Yeah, but pure pursuit runs, multiple steps to get to the goal point. So it adjusts the angle at each one. It would be a similar result, I think. Do you see what I'm saying?
Yeah.
Pure pursuit, you calculate the distance and the angle that you want to go, Okay, and then you do a step, you get your new pose, and you recalculate that steering angle. And if you integrated them, you get a path like that, like you're seeing. I don't know. I'll read your write-up later.
Yeah.
I was just trying to understand this. It was confusing.
Yeah, so like now that you pointed out, like it kind of like is similar to pure pursuit. Yeah. Like, so what we
Okay.
thought was like the difference where it will make it like isn't pure pursuit, like once we get the waypoint, it just like directly turns the steering angle towards that. In this case, like we were we thought like it's smoothing out, so it might make it a better way to control, like trace the trajectory.
Yeah. I mean, it is definitely smoothing. Yeah, there are some publications that treat the generation, like you can imagine that for a Bezier curve or a cubic polynomial, there's
Uh,
more than one polynomial parameterization that will get you to the same point.
like we tried the Bezier curves, like as we went through in the slides, but the problem was like so it was like so when we were implementing it, it was like it was like RRT star, like so we have a waypoint in front of us. It was switching between like two different or like splines to go there. So it was really confusing the car.
Yeah, so you can treat finding the parameters of your cubic polynomial as a MPC problem with the dynamics in it, but we can talk about that offline if you're still interested. Anyway, okay. I just wanted to clarify this point. I think maybe other people had questions.
Yeah, so there are a few questions in the chat. Um, when so about the assumption that the opponent goes on a pure pursuit centerline trajectory, yes, we did test it with like the different trajectories that we had generated for ourselves. So what we noticed was when the opponent car was on a trajectory that was very close to the wall, like the center L wall, we were not able to overtake the car because like most of the time we were overtaking from the inside, and so that was one thing that we noticed. But if the opponent car was following a trajectory that was on the outer sides, we were easily able to overtake the opponent car.
Do you have backup if your prediction is wrong? So it's a pretty strong assumption to just say that the opponent will always try and track the center line. Right, and so if you're checking collisions based on that alone, you could make a mistake. Is there any other mechanism that you're using to prevent collision? And I think really
Like
this is a question for all teams, but you're on
so
deck
like
right now.
backup in the sense, so like so our time horizon for prediction was like not that long, so there was always a gap which was collision free, so it will take that one. So like we did not have a backup for this, but we did not came across a situation wherein like this prediction method gave us like collision.
But so let's say you don't get any gap. What will happen then? What happens if it's infeasible?
Yeah, so like so that's what happened in the end. Like so when we were using MPC, the gap was like very less, so it was giving infeasible solutions. So like so the low speed mode which Achilles told about, like we were like significantly lowering the velocity with the car was moving in when the opponent was too close. That did help, but then yeah, like so the problem was still there. So mm,
Yes. So I know at least the agents that Billy and I made, and then some other people's agents, they would just slow down or stop if everything's infeasible. Which, I mean, it seems like now that we're hearing about this problem, it seems like the right thing to do. But yeah, I'm just wondering if anybody had any creative solutions for that.
mhm.
Let's see. So I think are there
Yeah,
other questions?
yeah. So there's a question by David, like which asks, did you incorporate the prediction into the MPC formulation? Or treated yeah, so it was treated as static obstacle. So the waypoint which you got to go at was after doing the collision check with the predicted path. So our MPC did not have to deal with the prediction of the opponent. Never tried MPC with raw RRT path. No, so that we had planned initially. So our backup was using RRT path as the reference trajectory for the MPC. But even in that case, RRT will give a jagged path, so we'll have to smoothen it out. So we thought why not directly just use Dubin's path and Bezier curves to so our initial plan was using Dubin's path. We spent quite a lot on that, but it did not work out in the end because it was giving sometimes very weird trajectories. So we ended up using a very simple approach because we did not have much time to try it out. Is it sampled regularly? What intervals? What part was this about?
I think it's the blue dots on the green path for your reference trajectory generation. I'm pretty sure.
Yeah, so for that we were sampling for I think 10 time steps. So the horizon for the predicted path in the MPC was the same. So in that you can see the blue dots are the path given by the MPC tracker, and the green is the behind that is the reference trajectory.
Okay, I think maybe that's all the questions. And again, thank you for all the work. It's pretty impressive how much everybody has gotten done given the circumstances. So thank you.